WhatsApp chat group. Okay, so yesterday we had some motivation about sequences and the definition of convergence of sequences. Why do we need to do sequences? Exactly where we are mostly interested in this semester and all these things. Now, um, so the next thing what we have with us is this thing, that limit of a convergent real sequence is unique. Um, so the proof goes like this: let xn be a sequence of real numbers converging to two real numbers, x and x dashed. We will show that x is same as x dash. That is, the limits are same. Now choose any epsilon positive arbitrary. Then by definition of convergence, for the chosen epsilon positive, we can find two natural numbers k1 and k2, such that for all n greater than or equal to k1, xn will be epsilon by 2 close to the point x. So mod of xn minus x is less than epsilon by 2. And for all n greater than or equal to k2, absolute value of xn minus x dashed will be less than epsilon by 2. So now if you choose k as maximum of k1 and k2, then for every n greater than or equal to k, both these inequalities, this inequality and this inequality will be satisfied. So absolute value of xn minus x will be less than epsilon by 2. Also, absolute value of xn minus x dashed will also be less than epsilon by 2. So hence, using the kth term, for which xk minus x will be less than epsilon by 2, xk minus x dashed is also less than epsilon by 2. So for that, we see that 0 is obviously less than or equal to, this is an absolute value, so this is always non-negative. So 0 less than or equal to x minus x dashed. This is less than or equal to, I am just using triangle inequality, mod of x minus xk plus mod of xk minus x dashed. And this is less than epsilon by 2. The first term is less than epsilon by 2. The second term is less than epsilon by 2. So this is equal to epsilon. So we have mod of x minus x dashed is less than epsilon. Now, therefore, x and x dashed are two real numbers such that for any epsilon positive, however small, the distance between them is smaller than epsilon. So therefore, we had already seen this result in the class, that if this happens, then there is no other way but these 2 points x and x dashed has to be same. There is no other way out. So therefore, x is equals to x dashed. So this proves that this is the limit of convergent real sequence is unique. Okay. So next up, any questions? Okay, so next up we have is what we the next part in the chapter of sequences is finding the limit. Now, as this is a sort of recapitulation course, other than the Kochi part, this is a recapitulation course. I will not be doing the entire all the proofs and all those things. I will be just giving you. I will just join the pieces. You know all the theorems, you know all the results, you have done sums, you have done most of the things to get marks. What I will try to do, I will try to give some context that whatever you have done, why have you done it? That is my only motivation to give over here till we reach Cauchy sequences. So today's class we'll try to do like that only. So you have done all these things. So finding the limit is my next section. So the problem with the definition of convergence of sequence is that that definition is not constructive. It is a verifying definition. You feed it with a number, it will verify whether the sequence converges there or not. It does not help you to actually find the limit. So in this section, we will see methods to find limits of a sequence. Method 1, the first one is the most obvious one, observation, which is basically common sense, nothing else. Here we guess the limit of a sequence and then use the definition to verify it. Very effective and practical, but boring to discuss, obviously. So like this one, this this one we have seen yesterday, this example, that over here this xn equal to 1 plus minus 1 to the power n divided by n, this sequence converges to 1. So we guessed that this sequence converges to 1. That guess is very much viable because we have this something a constant, a bounded quantity divided by n, so this will be tending to 0, so this converges to 1. So this is our guess. This was our guess, and we used this definition that our guess was correct. So that is what we this observation observation method does. We guess this thing. Ilma, right here only, right in the WhatsApp group. Right in the WhatsApp group. Okay. So the first method is by observation. That is obviously the very practical and effective, but obviously boring to discuss. There is nothing to teach you over there. Now the second method is for a monotone sequence. The second method is for monotone sequences. A sequence is monotone, xn is monotone if for all term n, x n plus 1, the n plus 1th term is bigger than or equal to nth term. In that case, we call the sequence a monotone increasing sequence, or for every nth term, we have the n plus 1th term is smaller than or equal to nth term. Then it is monotone decreasing sequence. Excuse me. So let me put a small remark. Sometimes we call a sequence ultimately monotone if the sequence is the monotonicity of the sequence occurs after first finitely many terms, like xn plus 1 greater than or equal to xn. This happens for all n greater than or equal to 100, n greater than or equal to k, let's say. Then we say it ultimately monotone. Okay. This is just extra nomenclature in this regard. Because since we are always interested in the behavior of tail of a sequence, so ultimately monotone is basically monotone only. So we have the following result for the monotone sequences. A monotone increasing sequence bounded above is convergent and converges to its least upper bound. So this result we have also already seen in the last semester. This theorem actually gives us a way to find out the limit. You take the sequence, if it is monotone increasing sequence, you find the least upper bound of that thing, then that will give you the limit of that sequence. So this is how we find the limit of a sequence. So some examples, the sequence 1 plus 1 by n whole to the power n is both increasing and bounded above. You have seen the proof of this fact in last semester only. The above theorem says that it is convergent. we call the limit of this sequence E. Okay, now something to remember over here, it does not converge to E. It converges and we call the limit as E. Okay, so E is defined as the limit of this particular sequence. We can by this theorem, the above theorem guarantees that this sequence is convergent, and the limit of this sequence is defined to be E, to be the number E. When we do that, then we have the same theorem guarantees that this sequence xn is equals to 1 plus 1 by 1 factorial plus 1 by 2 factorial up to 1 by n factorial. This thing converges to the same limit E. Here I do not have any problem in saying converges to E. But in this case, it does not converge to E, it converges and we call the limit as E. But over here, if when we have defined already E already over here by the limit of the sequence, we can show that this is the limit for this sequence as well. This above theorem shows that the sequence xn, where xn, that infinite radical what we talked about in the very beginning, x1 is equals to root 2 and xn plus 1 is equal to root over square root of 2xn converges to 2. So yeah, this also shows helps us to prove that. Now we have the following obvious corollary to this theorem, just the opposite of this thing. The monotone decreasing sequence, increasing, this is decreasing. Decreasing sequence is bounded below, is convergent and converges to its greatest lower bound. So next, third method, we have the limit theorems. So that if we know limits of individual sequences, we can find out the limits of derived sequences as well. Okay, we have this following theorems. First theorem says xn and yn be two sequences so that both are convergent. Xn, the sequence xn converges to x and the sequence yn converges to y. Let C be a real number. Then limit of C times xn, that is a new sequence, is C times x, that is C times limit of xn. So this constant multiplier C can go outside the limit over like this. C over here is inside the limit and here C is outside the limit. So C can go outside the limit provided the limit exists, the sequence converges. The limit of xn plus minus yn is x plus minus y. So the limit breaks algebraically. So limit of xn plus yn, limit breaks to them individually. Limit xn plus limit yn. Limit xn minus limit yn. Just like that. This is also true for multiplication as well. Limit of xn into yn is xy, limit xn into limit yn. And this is true for ratios as well. Then xn over yn is x by y, that is limit xn over limit yn, provided of course yns and y are not 0. So all these theorems are basically based on, keep this in mind, they are basically based on the assumption that the sequences in the context that is sequences xn and yn, both of them are convergent. If you do not have the convergence of them, then these results do not hold. Okay, so that is something you must be very concerned about. It may come like limit x, if you choose xn to be n, yn to be minus n, then xn plus yn will be constant sequence 0, but there is no the individual sequences xn and yn, they do not converge. So this algebra of limits will not be possible in that case. Next up, we have sandwich theorem. You all know what does it do. we have three sequences xn, yn, and zn, such that yn is sandwiched between the sequences xn and zn. Xn less than or equal to yn less than or equal to zn. And if it happens so that xn and zn, they tend to the same limit L, they tend to the same limit L, both of them, then the sequence yn has no other option but to converge and converge to the same limit L as well. So this is sandwich theorem. So next up we have this theorem that if xn be a sequence of positive real numbers, then if the ratio of the term ratio sequence, we call it term ratio sequence, xn plus 1 over xn, the ratio of the n plus 1th term and the nth term. If that is L, then depending on the value of L, if L is less than or equal to and greater than or equal to 0, less than 1, because definitely L cannot go beyond 0, they are all sequence of positive numbers. So then xn converges to 0, and if L greater than 1, then xn diverges to infinity. We will define what is diverging to infinity in a moment, probably in the next class. I probably have not prepared the slide for divergent sequences. Anyway, so the next thing is, if nth root of a sequence converges to L, then depending on the value of L, if L is smaller than 1, then xn converges to 0. If L is greater than 1, it diverges to infinity. In the both cases 1 and 2 above, the case L equals to 1 is inconclusive. You have seen proofs and all these things in the last semester. I'm just trying to give you some context, that on which context why you had to learn these theorems at the first place. Next up we have Cauchy's first limit theorem. If we have a sequence which converges to x, then the arithmetic mean sequence of first nth term, so that is x1 plus x2 plus up to xn whole divided by n. This is the arithmetic mean of the entire of first n terms. So this sequence also converges to the same limit x. There is Cauchy's second limit theorem. Xn be a sequence of positive reals and the term ratio limit goes to L, then the nth root of xn, this limit also goes to L. So all these theorems helps us to find the limits of a sequence. So that is what we do over here, that because the definition of convergence relies on the fact that you have to provide a number to it to verify the limit. The definition cannot tell you that how to find out the limit. This thing is a so all these theorems what you have done so rigorously in the last semester, they all make your life easier, in the sense that they help you to find the limit of a sequence. And once you guessed or guessed the limit of a sequence, then it will be the definition can verify it for you, or the second and third method what we talked about, that is that will help you to find the limit without any problem. So that's it for today's class. I just made a very small number of slides today. So if you have any questions,